we're going to explain a new chapter, which is the photoelectric effect. To show evidence of this phenomenon, we perform the following experiments. In the first experiment, we bring an electroscope and place a zinc plate on it. The setup is negatively charged, so the leaves are separated by a certain angle alpha. The zinc plate is illuminated by an ultraviolet lamp. We notice that the angle between the leaves becomes smaller. This means that the setup lost some of its negative charge. In the second experiment, the zinc plate is illuminated by a bright incandescent lamp. The angle alpha between the leaves remains unchanged. That is to say that the electroscope hasn't lost any of its electric charge. The electroscope preserves its electric charge, so the radiation emitted by the incandescent lamp was unable to discharge the electroscope. In the third experiment, the setup is positively charged. The angle between the leaves is alpha. The zinc plate is illuminated by an ultraviolet lamp. We notice that the angle alpha remains unchanged. So the electroscope doesn't lose its charge, it preserves it. In the fourth experiment, we placed between the ultraviolet lamp and the setup a glass plate. We notice that the angle between the leaves remains constant. When replacing the glass plate by plexiglass or quartz, we notice that the angle between the leaves decreases with time. So what can we say about the fourth and fifth experiments? The glass plate blocked the ultraviolet radiation from passing to the other side. Whereas the plexiglass or quartz allowed the ultraviolet radiation to pass through the other side. And as a result, the setup will discharge. By returning to the first experiment, the electroscope is surrounded with glass. The ultraviolet radiation is unable to penetrate the glass. And as a result, the discharge of the electroscope will happen from its upper part only, specifically from the zinc plate. Thus, the zinc plate will lose its negative charge, and as a result, the zinc plate will emit electrons. In the second experiment, the zinc plate won't emit its electrons when illuminated by an incandescent lamp. Hence, not all radiation are able to extract electrons from the zinc plate. This brings us to the definition of the photoelectric effect. So what is the photoelectric effect? The photoelectric effect is the emission of electrons from a metal that is illuminated by convenient radiation. This is the definition of the photoelectric effect. Back to the third experiment, the ultraviolet radiation was unable to extract electrons from the zinc plate because the electrons were being kept in place by the attraction of the positive charges that are on the zinc surface. For that, we notice that the charge of this setup remains conserved, and as a result, the angle between the leaves remains constant. To study the photoelectric emission by a metal, we use the photoelectric cell. A photoelectric cell is made of a quartz bulb that is emptied from air. Inside the bulb, we find two electrodes, the cathode and the anode. This is the cathode, The cathode is a certain metal that is curved in a certain shape, and this is the anode, that is a metallic rod that faces the cathode. The experimental study of the photoelectric emission is performed as follows. The photoelectric cell is connected to a DC generator of adjustable voltage. In series with the cell and the generator, there is a microammeter to measure very small electric currents. Furthermore, a monochromatic light source of adjustable wavelength is used. The light source illuminates the cathode. It illuminates the cathode with a radiation of wavelength lambda. The ammeter indicates the flow of an electric current. Hence, the wavelength in use is less than a certain value that is called the threshold wavelength. Threshold wavelength. In this case, the electric current is non-zero. But if the wavelength is greater than a certain value, the ammeter doesn't indicate a flow of the current throughout the cathode's exposure time to the radiation. That is to say, it is impossible to get an electric current in the circuit for a wavelength value greater than lambda 0. Only when the wavelength is less than a particular value, lambda 0, that is the threshold wavelength. If the cathode is made of cesium, the threshold wavelength is 0.66 micrometers. If the cathode is made of calcium, the threshold wavelength is 0.45 micrometers. If the cathode is made of potassium, the threshold wavelength is equal to 0.54 micrometers. This shows that to each metal there corresponds a specific threshold wavelength. The threshold wavelength is a characteristic of the metal only. So how can we interpret the existence and non-existence of the current in the circuit then? The bulb plays the role of a quartz switch. The anode and cathode are not electrically connected. When the cathode is illuminated by light of wavelength less than lambda 0, an electric current is detected by the microammeter. This means that the open switch becomes closed. Radiation, and upon striking the metal surface, extracts electrons from the cathode, which in turn reach the anode. This radiation is capable of extracting electrons from the cathode. The electrons become free, and due to the presence of an electric voltage between the two electrodes, the anode being positively charged, whereas the cathode being negatively charged, the cathode repels the electrons and the anode attracts them by an electric force. This force will guide the electrons from the cathode and towards the anode. When the electrons leave the cathode and reach the anode, now the circuit becomes closed and An electric current will traverse the circuit. The ammeter will then indicate the flow of an electric current. In the second case, if lambda is greater than lambda 0, I is equals 0. This means that no electrons are extracted from the cathode and the photoelectric effect is not achieved for lambda greater than lambda 0. Note that no matter how long the cathode is illuminated, as long as lambda is greater than lambda 0, the photoelectric effect does not appear. But in the case where lambda is less than lambda 0, as long as the radiation illuminates the cathode, there will be emission of electrons. The photoelectric effect is a quasi-instantaneous phenomenon. It is a phenomenon that is realized almost instantly. Quasi-instantaneous means almost instantly. So the photoelectric effect is a quasi-instantaneous phenomenon. As soon as the radiation illuminates the cathode, electrons will be extracted. To extract an electron from a metal, we need energy. The minimum value of this energy that is capable of extracting an electron from the metal is called the extraction energy. It is denoted by W0. The extraction energy, W0 of a metal, is the minimum energy needed to extract an electron from a metal. This energy is also called the work function or the ionization energy of the metal. Note that this extraction energy is not the same for all metals. Some electrons are strongly bound to a certain metal, whereas in other metals they are not. Let's take some examples here. For cesium, the extraction energy is 1.88 electron volts. The electron volt is a unit of energy, such that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. For potassium, the extraction energy is equal to 2.3 electron volts. For calcium, W0 equals to 2.76 electron volts. What do we notice? We notice that the extraction energy, which is the minimum energy for extracting electrons from a metal, for cesium for example, is 1.88 electron volts. For potassium, it is 2.3. For calcium, it's 2.76. Then the electrons are more bounded in calcium than the electrons in cesium.